So what is logistic regression? So before we get into the detail, let me try to bring up something. So what is the equation that we arrived at for linear regression with one dependent variable and one independent variable? What is the equation that we arrived at? A generalized form. Y equals mx plus c. Or to be more specific, y is equal to beta naught plus beta 1 x1 plus here. Okay, this is the generalized form that we arrived at in terms of linear regression. So what is y here? The dependent variable. When we say dependent, is it a continuous variable, or did we see a dichotomous variable, or what was that in logistic linear regression? Continuous, right? It was a continuous variable. And what is the dependent variable that most of the time we saw continuous, and also try to pick up dichotomous as dependent variable. So actually the independent variable could be continuous, nominal, or ordinal. Okay. So what we are trying to do now is understand logistic regression in terms of linear regression. I would like to say that logistic regression is a special form of linear regression. I would like to put it that way. The equation is still going to be something similar to y is equal to mx plus c, but when you say a dichotomous, y is dichotomous here, y is not continuous, y is dichotomous, that means you will have yes or no or 0 or 1 as the dependent variable. So how do you think you will get a plot if if you're going to plot linear regression? How did we arrive at the plot, or how did it look like? It looked like something like this, right? It looked like something like this. It could be something the other way or as well, like probably something like this. Anything is okay. So this is how we get the equation. When you represent this equation, this is how you would get the regression line. Okay, but in logistic, just imagine what will be the values or dependent values. It is going to be y is going to be 0 or 1. And still you try to plot something like this. Where is 0? 0 is here somewhere. And 1 is somewhere here. So always you're going to get between 0 and 1. If it could be either a 0 or 1, that is what you would be getting. So what happens is, for various values of x, when you get the value of y as 0 or 1, your values, something should, either it should be here, I'll put it as x, or it will be here. Okay, so this is a problem actually that we need to address. So we are going under the assumption that the logistic regression will also have a similar representation, y is equal to mx plus c. But when you consider y, it is going to be either a 0 or 1, and that means there is nothing in between here. So that is what will be your, these are the observed values. These are the observed values. The observed values will always be a perfect 0 or a perfect 1. You want to say yes or no, high or low, something like that. It is dichotomous. So you're going to observe like this. And in this case, how do you think the regression line would appear to be? The regression line, if you draw, maybe it appears like this, right? So this is how it is going to appear. So what is the inference or interpretation that you're going to make for all the observations that you predict to be falling on this line? You just imagine the situation. We got a problem here. What will be the interference? If it is going to be here, something here, this could be a predicted value. That's what the line says. But the observed value is always here. It is at 1. There is nothing in between. So the perfect case, and moreover, this particular region, we can understand that it is still within the limits of 0 and 1. Whereas you take this particular region, it goes off limits. This is another problem. So these are the issues that we have when we try to plot or try to pictorially see a logistic regression in terms of our assumption that it is a similar expression as we have in a linear regression. So how do we uh, circumvent this particular region and this particular region? So logistic regression, we would like to see at least like this, something like this. We don't want to see overshooting. 0 and 1. If the plot is here, this is the 0 line, the 1 line, then that's the 0. We don't want it to overshoot. At least we say it tends towards this, so that it is 0 here. After this is one particular x value, independent variable. Below this x, you can call it as 0. And above this x value, you can still call it as 1. So this is an ideal situation, ideal expectation out of the regression line. Okay, fair enough. So in order to arrive at this, if you take the y variable or the independent variable as 0 and 1, you will still trying to figure out how to represent this. This is one problem. Like, you need to level it off. You can't extend it beyond the 0, because there is nothing to be captured beyond 0 and nothing to be captured above 1 as well. It is going to be 0 and 1, yes or no, something. So logistic regression does not deal with direct dependent variable, but a expression or a extrapolation of that dependent variable. What is the extrapolation? We would like to say, instead of 0 and 1, we would like to see the probability of getting a 1. Okay, understood? When we say that, that means this is the probability of 0.5 0.5. Okay, so this is 0.5. That means this is 50% probability. We are going to represent y in terms of probability here in logistic regression. We understand the dependent variable, the observed values or the actual values are going to be between 0 and 1. But what we are trying to plot is not the prediction based on the observed values, but the prediction based on the probability of getting a 1. So that way we are still okay. If you find an observation on the regression line, somewhere in the middle, that means you're going to say there is a 50% probability of getting a 1. If there is a point on the prediction line somewhere here, and this corresponds to 0.75, and I'm going to say there is a 75% probability of getting a 1. That is all I can say. Okay. So this value, so these values, though the predicted observed values, they may have a prediction of something like this. Okay. They may have a prediction of maybe 0.8 here. So this means though it is 1, you're going to say there is 80% probability of getting a positive answer or a 1 or a yes. That is how we are going to look at regression, logistic regression. Okay. So you know the linear regression, it's represented by y is equal to b naught plus b1x. And if it is a multiple linear regression, we did see that b naught plus b1x, 1 plus bnx, n up to bnx, and where n is the number of independent variables. So this is a generic expression. So in terms of extrapolating, now we know this is a case of linear regression. When you draw a line through it, it's going to be something like this. You draw a best fit line. We took the same example and we did a linear regression, salary versus experience, and we got a line similar to this. But this is okay. But if you want to extrapolate the same understanding to logistic regression, how does it look like? So this is our linear regression line. We understand this example perfectly, but when we say a logistic regression, as I had explained, the red cross you see here are always the observed values. That means it will be a perfect 1 or a perfect 0. So this is how it's going to look like. And when you're going to draw a regression line on this observations that you obtained on a dichotomous dependent variable, it's going to be, you can expect it to draw something like this. That's what we have seen. But we know that that's not a good fit. That's not a best fit line, just because primarily because of two reasons. One, it overshoots the 1, and it also undershoots the 0, and there are no values on the line, on the regression line, where you predict something, but you don't see actually any observed values falling on that. Okay, so there is going to be a big gap on that. So first thing what we do is we make this line to fall in line with the 1. That means we don't allow it to extend beyond 1. So what we do, this particular portion and this particular portion, we try to make it in level with 0 or in level with 1, as the case may be. So what we do, how it look like, we just make it this way, so that at particular value of x, for example, at a particular value of age, we always see it is perfectly aligned to the 1. And here it is below a particular value of age, it is perfectly aligned to 0. That means always you're going to expect 0 or no. When if it is yes or no, it is no. That's what you're going to expect. Now, coming back to the problem, still we have not arrived at, we know what is the expected line, how it should look like. But what is the equation that supports it? If you draw a equation based on this, if you draw a regression line based on this equation, you're still going to get something like this. But you need to come up with an equation which supports this particular line. it looks like a sigmoid curve, like something like an S curve. Okay, something like this, something like this, something like this. It looks something like an S curve. If you take y is equal to b naught plus b1x, you will always get a straight line. Okay. Now the same y, you represent it in some other way so that you get a sigmoid curve like this. What is the best way to represent? 1 by 1 plus e minus y. Okay. So this is a hard part to understand, in the sense, like, if you know how you got this, then you are good enough to proceed further. But if you really don't understand this particular thing, then most of us will be in the same boat. Like, I mean, how did we arrive at this particular representation of y instead of a direct y? So so let's consider this one. 1 plus e minus y is also another way of representing y. There are no other variables here inside this expression. Okay, if this is y, this is also a representation of y. You just need to represent it so that you get a curve. But what happens is, this is also an expression for the probability. Okay, so what we are trying to express here on the y-axis is not the y, but the probability of getting a y. So that is what we are trying to express. So as of now, you just need to take it on the face value that y can be represented in terms of 1 by 1 plus e minus y, and that is also the formula for probability of the getting a positive or a yes or a 1 on a y. So that is what it means. So once you have converged on this, then it becomes easy to proceed further. Okay. So what we did is, we don't write a y directly for y-axis. We do a 1 by 1 plus e minus y. So that is the probability. So that is the simple explanation. So again, now you know, now you get y. Instead of y, this is what is y now. This particular equation, if you evaluate, this is antilog, okay, e is called the exponential or the antilog. If you take a natural log and you find the value of y, then it will be, this is the equation. Okay, natural log of p by 1 minus p. Okay, so that will be the y. So if you represent the natural log of odds, so you can also call this p by 1 minus p as the odds. Okay, ODD, yes, odds. O D D, yes. Okay, this is called odds, p by 1 minus p. What is p by 1 minus p? Probability of event to occur, and by divided by the probability of the event to not to occur. 1 minus p is the probability that an event will not occur. So that is as simple as that. So with this, now we are almost good to go ahead. Now we have represented the equation in terms of the odds, the natural log of odds. So that is the y. That is the new y. So the y is not going to be actual dv here on the y-axis. It's going to be something, you can call it probably probability now. Okay. And what is it expressed as? P hat. P hat is the probability of the y to occur. Predicted values. P hat is the predicted values. Okay. So now, how do you interpret this graph now? Now that you got a x-axis with the independent variable, and the y-axis, you know, you're going to express the predicted probability. So how do you interpret this? This is the case of an A. The example that we are trying to see here in terms of age. Probably you take this as an example that I'm trying to convey to you. Based on the age, the problem is, the business problem is, you have data, and this data contains a population or a sample with number of people whose age is captured, and based on their age, we are trying to decide whether they are likely to enroll for a particular program. That is all we are. As of now, let's consider that as an example. What we see here, as the age goes by or goes up, the probability of a particular candidate enrolling for a particular program is high. And after a particular age, probably if it is 50 or something, we are very sure that the applicant or the candidate is 100% sure of enrolling to the program. And similarly, if the age is 30 or below, let's say this point is 30, if 30 or below, then we are 100% sure that they are that they will not enroll to the program. I will say will not. I will not say even the probability of enrolling is 0. I would directly say they will not enroll. So that is the interpretation that we can make from this. So going by this example, now we have captured probability on the y-axis, predicted probability, and this is similar to that. So how do you interpret this? The 20 you see here. Similarly, 30 is the predicted values. The blue crosses are predicted values. That means predicted probability. And how do you extrapolate it to the y-axis? So you extend it or map it to the y-axis, you get a probability of 0.7. That is, people with the 20 years or less have only a 0.7% chance of enrolling into the program, whereas people who are 30 years old have a 23% chance of enrolling, 40 years old or 85%, and 50 years or above or 99.4%, or probably it's as good as 100% or a perfect one. Okay, so that is how you interpret this logistic regression curve. Now, initially we thought of plotting it in terms of actual DV, right? Actual dependent variable. Now we decided we are going to plot the predicted probability instead, not the predicted actual value. It is the predicted value, predicted probability. Okay. So that is the change that happens if you try to understand the logistic regression in terms of linear regression equation.
I'm sure you enjoyed learning from this video. Please like the video, and if you have any doubts regarding this video, please comment us in the comment section, and don't forget to subscribe to our channel for more such informative videos. Do look out for other related videos in our playlist. For more information, visit our website now. Keep learning with Intellipaat.